Good morning children, welcome back to your chemistry class. So in the last video we had discussed about the principal quantum number and the azimuthal quantum number. In this video I am going to talk about the magnetic quantum number and the spin quantum number. Clear? So to begin with the magnetic quantum number, right? This magnetic quantum number is designated by the symbol M, right, to explain the splitting of the single spectral line into number of closely spaced lines in the presence of magnetic field. This is called as Zeeman effect. Followed? So the theory was proposed that an electron producing a single line has several possible space orientations for the same angular momentum vector in the magnetic field. Clear? That is, to understand, under the influence of magnetic field, each subshell was further subdivided into orbitals. I'll mention over here it was talking about the Zeeman effect. First and foremost, you should know what is Zeeman effect. It is the splitting of the single spectral line into number of closely spaced lines in the presence of a magnetic field. Okay, first and foremost you should understand this word, what I meant to say over here, that over here the magnetic quantum number, it explains the splitting of the single spectral line into number of closely spaced lines in the presence of magnetic field, which is also called as Zeeman effect. Right now, electron producing a single line had several possible space orientations for the same angular momentum vectored in the magnetic field. What do I mean by that? That under the influence of the magnetic field, each subshell is further divided into orbitals, right? So under the influence of a magnetic field, each subshell is further subdivided into orbitals. Clear? So magnetic quantum number, it describes about what? The orientation or the distribution of the electron cloud. Hence, magnetic quantum number, what does it describe? It explains the orientation. Describes the orientation, or in other words say the distribution of the electron cloud. Is this clear? Now, for few of the azimuthal quantum numbers, the magnetic quantum number may assume all integral values, that is from minus L to plus L including the 0. That is total what? Total becomes 2L plus 1 value it is going to show. Thus, let us see over here that when L, the azimuthal quantum number, is 0, then your magnetic quantum number is also 0. That is one value. 0 means, doesn't mean 0. 0 over here has a value. So I am mentioning it over here, only one value which is 0 over here, right? When your L is 1, then what is your M? M will be -1, 0, +1, right? That means 3 values are there, or we can say 3 orientations will be found over here. Here there is only one orientation, here there are 3 orientations, okay? Are you getting my point? So one orientation corresponds to only one orbital. This means one orbital. Okay. And 3 orientation means it is designated to 3 orbitals. Over here you will find 3 orbitals. So what could be those 3 orbitals? They could be like px, py and pz. So your subshell P has 3 orbitals x, y and z. Did you get that? So now if L is equal to 2, then what is your M? M will be equal to -2, -1, 0, +1 and +2. How many orientations? How many orientations? 1, 2, 3, 4, 5. So there are 5 values. That means 5 orientations. Is this clear? That means these 5 orbitals are designated over here. What are those 5 orbitals designated over here? They could be like D. Subshell D has 5 orbitals, okay? So it is dxy, dyz, dzx, then d x square minus y square and dz square. Got it? So over here you are going to find these 5 orbitals. Now if L is equal to 3, then M will be equal to what? -3, -2, -1, 0, +1, +2 and +3. Clear? So how many values? 7 values are over here. That is, it will have 7 orientations. I hope this much is very clear how to find out. This means different values of your magnetic quantum number. For a given value of your azimuthal quantum number, it provides the total number of ways in which a given SPDF subshell in the presence of magnetic field can be arranged in the space. Okay, so that is what I am going to show you. It will be arranged in the x, y and z axis, or you may say total number of orbitals into which a given subshell can be divided, that is your x, y and z axis. Now understand, when L is equal to 0. So what did I say? If your azimuthal quantum number is 0, then your magnetic quantum number is also 0. That means it has one value. That means it has just one orientation. Okay. That implies that S subshell of any energy shell has one space orientation. Did you get that? S subshell of any energy shell has one space orientation, okay, and hence it can be arranged in the space only in one way. Which one? Along the x, y or z axis. So I'll write it down over here. What did I say? S subshell of any energy shell has one space orientation, and therefore it can be arranged in space only in one way, okay, along the x, y and z axis. I'll show you over here. Thus we can say that this s orbital has a symmetrical spherical shape. Thus, very important, s orbital has symmetrical spherical shape. Okay, so now I'm going to discuss about the shape of the s orbital with you. So try to understand. This is your x-axis. This is your y-axis and this is your z-axis. Okay, clear? Now I'll explain you in detail about this s orbital. First and foremost, these s orbitals, they do not have any directional character. No directional character. Okay, these are few points that you should remember. They only have the spherical shape. They have spherical shape, right? Then the energy and the size of the s orbital, it always depends upon the value of n. That is what? The principal quantum number. That is the order of your principal quantum number. The energy and size of s orbital depends on the value of n. Okay. Next, the region where the probability of finding electron is 0 is always called as the node or the nodal surface. What? The region where the probability of finding electron is 0 is called node or nodal surface. Clear? Is this point clear? So in general, ns orbitals, they have n minus 1 nodes. Okay, and your L number of angular nodes or nodal planes. ns have n minus 1 nodes and L number of angular nodes. So if you want to see, this is a node, this is for 1s. Okay, then this is 2s. This is 3s. This is 3s. So where are the nodes? These are the nodes. This is the node. This is the node. Okay, then should say this is also the nodes. These are all the nodes or the nodal surfaces. These are the nodes or the nodal surfaces. Can you see this? These are the nodes, right? So this was all about your S subshell. Now let's talk about Next subshell. Now, when L is equal to 1, then what did we study? M is equal to what? Minus 1, 0, plus 1. So there are three values. Three values means three orientations. It implies that P subshell of any energy shell has three space orientations, or it has three orbitals, right? So each P orbital is always a, this is your p orbital. We are talking about the p orbital, and the shape of the p orbital is a dumbbell shape. Okay, it is of a dumbbell shape. I'll explain it to you just now. So each one is a symmetrical along with the three axes. Okay, and it is always a directional character. So I'll show it to you just now. So let me write it down over here. Orbital, it is M. So what are those three orbitals that you're going to see? It is Px, Py and Pz. Pz will always be 0. This is plus minus 1. This will also be plus minus 1. Okay. So the first point is that it shows directional character. Okay. Second point, I have already told you that it has a dumbbell shape. Why do we get this dumbbell shape? Because the probability of finding the p electrons, it is maximum where? In the two lobes of the opposite sides of the nucleus. Thus it gives the dumbbell shape. Okay, so for any given value of n orbitals, this px, py and pz, these have equal energies. They have directional character, and the energy and the size of the p orbitals, this increases in the following manner. How? It increases like this: 2p, 3p, 4p, 5p and so on. So in general I can say that np orbitals have n minus l minus 1, or in other words you can say n minus 2 spherical or radial nodes. Okay, and l angular nodes. Clear? Now see the shape of it. If this is your axis, I'm first drawing you the axis. This is your x-axis. This is your y-axis, and this is your z-axis. Then in this case, if I want to draw this, is the structure of your px, because it is on the x-axis, right? So the nodal plane is what? YZ. Okay, let's see the second one. This is your x, this is your y, and this is your z axis. Clear? Then in this case, this is your p y y, because it is on the y axis. So this is the nodal plane x z, x z, right? And the third one, this is y, this is x, this is z. So Okay, so this is what, since it is on the z axis, so it will be pz, and the nodal plane xy. I hope this is very clear to you. The p orbitals are clear, the shapes are clear, the dumbbell shapes of three types, px, py and pz. Why are they called px, py, pz, and what is the nodal plane? Everything is clear. What shape do they show? Dumbbell shape. They show directional character. Then NP orbitals have n minus L minus 1 or n minus 2 spherical or radial nodules and L angular nodules. Okay. We next move to the next orbital. Now, when L is equal to 2, then M is equal to minus 2, minus 1, 0, plus 1, plus 2. How many orientations? 1, 2, 3, 4, 5. 5 values of 5 orientations. Is this clear? So this means that the subshell of any energy shell has 5 orientations. So here you are going to see what? The subshell, and it has how many orientations? 5 orientations, or in other words we can say they have 5 orbitals. Clear? All these 5 orbitals, they are not identical in shape. None are identical in shape. This much you should remember. So what are the different types of d orbitals? I'm going to write down over here. They are like d xy, okay, then d yz, then d zx, then d x square y square, and d z square. Okay, out of this, the first 4 of them, this is 1 2 3 4 of these, right? 4 of the d orbitals, they contain 4 lobes. They contain how many? 4 lobes, whereas this one, it contains only 2 lobes. Only 2 lobes. That all I'll explain to you just now when I'll show you the diagram. So the lobes of dxy orbital, they always lie between x and y. Okay. The lobes of dyz, they are going to lie between y and z, between z and x. Now, 4 lobes of dx square minus y square, where are they going to lie? They will be lying along the x and the y axis. Okay, while the 2 lobes of z square, they are going to lie along the x axis, and they will also contain a peculiar property, that is the ring of the negative charge, which will surround the nucleus in the xy plane. So I'm going to draw for you and show it to you over here. So look at this. This is your z axis. This would be your x axis. This is your y axis. So I'm going to first draw dxy. So what did I say? Where will you find them? On the x axis, and they are double. Is that clear? So your dxy, where are the 2 dumbbells found? They are found between x and y or axis. Okay. Now let's see the second one. This is your y, x and z. So now now I'm going to draw d, y, z. Between y and z we are going to observe. Okay, so here is one, and this side, this is one dumbbell and this is another dumbbell. Okay, so where is it found? Between Y and Z. This, can you see? It is forming the double dumbbell. Then X, Y and Z. Okay, so this one is your DZX. That means the dumbbells will be formed between the Z and the X axis. Okay, this is the shape of the DZX. Now let us see. This is X, Y and Z. So here, where are you going to see? One is over here. Okay, and one is over here. So is to be shown like this. So which one is this? This is dx square minus y square, right? And the last one is somewhat like this. As I had told you, it forms a ring. Okay, so here is the ring that will be formed. This is your x, this is your y, and this is your z axis. And which one is this? This is dz square. What did I tell you about dz square? That the orbitals are lying along the z-axis, right? And they also contain a ring of negative charge which surrounds the nucleus. Is this clear to all of you? So these were the 5 orbitals of your d subshell, and these are the figures that you need to understand over here. Now next we come to the spin quantum numbers. Let's talk about now spin quantum number designated by the alphabet S. So when the spectral lines of hydrogen, lithium and sodium, etc., they were observed by means of instruments of high resolving power, and each line was found containing a pair of lines which were called as doublets. Okay, so to account for these doublets or for these pair of lines, it was suggested that the electrons, while moving round the nucleus in an orbit, it also spins about its own axis, right? Either it spins in the clockwise direction or it might spin in the anti-clockwise direction. So we can say that there are two possible values. Either it spins plus half or it spins minus half, depending upon the direction of the spin. So if these spins are also known, they are also shown by the arrows, like upward arrow or the downward arrow. They can be shown like this, or we can also show it like this when both are together, right? So when do we show the upward arrow? Upward arrow, which also means plus half spin. Okay, this is your clockwise. When the electron is spinning clockwise, then it is your plus clockwise movement. When the downward movement is there, when there is downward arrow, right, then it is minus half, which also means it is moving anti-clockwise. I hope this much is clear. Thus, the spinning, it always produces an angular momentum. Okay, spinning produces angular momentum, which is equal to, we denote it by the alphabet mu, and we write down s over here. Okay, and this is equal to under root s plus 1 h upon 2 pi, and therefore the total spin is always equal to n into half. Okay, over here what does n mean? N means number of unpaired electrons. Number of unpaired electrons. Okay, now the electrons with the same sign of spin quantum numbers, they are said to have parallel spins. Parallel spins how? Like this. Okay, these are what? Parallel spins. So when do we find parallel spins? When there is same sign of the spin quantum numbers, then they show parallel spins. While those which have opposite signs of spin quantum numbers, they are always going to show the opposite signs. What are the opposite signs? They are going to show it like this. This is the opposite spins. Clear? Since the spinning charge is associated with the magnetic field, right? An electron must always have a magnetic moment associated with it, and therefore the paired electrons, they are cancelled out, and only the opposite spins, they are seen, right? The opposite spins show magnetic moment and develop a mutual magnetic moment. Is that clear? So I wind up over here for today. Next time I'm going to come up with certain important principles. Thank you.